Sir, morning, sir.
Please allow the people. Okay. I keep you as the co-host. Okay. So is it visible?
Yes, sir. Visible,
sir.
sir.
Yes, sir.
So yesterday, in the last class, not yesterday, we started with Cascode. Am I correct? Cascode we started.
Yes, sir.
Yes, this is. How గారు మీ co-host మీరు తీసుకోండి సార్.
Sir, 11 participants.
So now see Cascode. In the last class, we discussed about the Cascode. What is the beauty of the Cascode stage? So in the Cascade, it is simple thing. We have two types of configurations. So generally,
అమ్మను గట్టిగా అర
so with the single stage, I think single stage amplifiers, single stage transistors, we could not achieve what is our requirement fully. So our targeted achievements is difficult to get from the single stage. So now we should go for the what to take the multiple stages based on the requirement. Okay, based on the requirements, mostly we are talking about the gain. So gain of the single stage MOSFET is very small. We cannot satisfy the requirements of the design fully. So that mostly MOSFETs may be cascaded and cascoded. Two configurations are there to increase the gain. Actually, there is a lot of difference between the cascade and cascode in the BZT, multi-stage amplifiers. But whereas in the case of MOSFETs, because of their construction facilities, okay, the cascade and cascode is a little bit different. Generally, cascade definition, so the stage, that means one stage output is fed to the immediate stage as the input. That is a cascade. And cascode means we simply say that one transistor may be sit on the another transistor, head of the another transistor, or over the another transistor. That is the simple definition to keep remember in our mind. When it comes to the practically, the things will change. The things means here what? Very simple. Gain, impedance, either input or output impedance. These are the things very important. Here, the definition of the cascoding, I can say in such a manner that cascading of the two transistors. Here, the two transistors means what? One is the CS stage, one was the CZ stage. CZ, okay. So whenever the CZ, that is common gate, okay, common gate is connected. CS stage, both are connected in cascading mode. That is called the cascode. I think this type of definition, this type of what is it one, statement you cannot find in the BZT. But here is the beauty because so here is the two transistors are there. One is the M1 transistor, one more is the M2 transistor. Okay, so M1 is sitting upon the M2. Clear? So the cascading of CS and CZ is called the cascode. Cascading of CS and CZ is called the cascode. So I think cascading is nothing but series connection. Cascoding is nothing but parallel connection. Okay. So, but here is see, CG is sitting upon the CS. So that is the what? You can say there is a cascoding. Yeah, M1 generates a small signal drain current as we discussed in the last class. So M1 is the current CS stage. The CS stage input is the voltage, output is the drain current. Okay, input is fed to the gate of the transistor, and output is the current which flows in the drain terminal or from drain to source. Okay, so purely I can say that your CS amplifier is a input signal is the voltage signal and output signal is the current signal. Whereas it comes to the CZ, common gate stage. So the common gate stage, the input signal is the current signal and output signal is the voltage signal. Yeah. So whenever you are connecting cascoding of both CS and CZ, what happened? The current which is produced by the CS is flowing or fed as the input of the CZ stage. So that you should be remembering on it. So that's why what happened? The CS and CZ stages are connected as cascode. Okay, so definitely whatever the current produced according to the input signal by the M1 transistor will be routed by the your M2 transistor, that is the CZ stage. Okay, and which will make to produce will establish the drop across the RD, which can be treated as the output voltage. Okay, from this story, if you consider the whole circuit as a single, so what is it? One input is voltage and output is voltage. How beautiful this looking circuit. Okay. Anyhow, so we want to do the some analysis for the this cascode stages. Analysis means I think it is not more than that finding of the voltage gain and resistances both at input and output sides. And one more thing I told you, I shared out with the last class with you. That is this type of configuration is called the telescopic. Telescopic. Why it's called the telescopic? Okay, I will keep this word so aside to discuss later more. Okay. Yeah, my question is now, what happened if the value of VIN, that is input voltage, or the biasing voltage, or fixed bias voltage, which is applied to the gate of the CZ stage, changes by small amount. So, as a whole circuit, if you take, any changes may take place at either input at or the biasing point. What should be the consequences will it face? Okay, what happened if the values of VIN or VB? What is the VIN? The input voltage applied to the CS stage. What is the VB? The biasing voltage applied to the gate of the what is it to keep the input transistor in the saturation. Okay. So what happened if both any one changes small change in voltage? Yeah, we will discuss that. What happened if the voltage changes by a small amount at both these terminals, either at any one of the terminal. Okay. So for the simplicity, I think you should bear with this. Assume both the transistors in the saturation, both CZ and M1 and M2 transistors. Don't say CZ and CS. Okay, M1, M2 transistors. So assume that both are in the saturation. And one more thing, lambda and gamma. Gamma is the body effect coefficient, and lambda is the channel length modulation factor. So both will assume 0. Okay. So if you are assuming both are zeros, and if you treat it as both the devices are in the saturation, you can I think do the analysis in the following way. See, look at this picture. In this picture, so I think this is the same thing. Just I have dragon means both the devices and kept all the devices in one side, so that here this is the M1 device. As you said, this is CS test. This is the M2 device. This is the CZ test. Okay. So here is the input is applied. Here is a fixed bias voltage is applied, and you are correcting the output here. But before that, this is the X. X is the node which joins the M1 drain and M2 source. So what is the changes of the voltage? What amount of voltages changes at this point of X or at this node of X we need to find. So if you have any doubt, please raise your voice, no problem, in the middle also. But anyhow, so the same circuit I have drawn like this. Okay, nothing wrong. So nothing modified. So just I want to keep gate terminals one side and other terminals are outside. Okay. So Listen. Yeah, my question is what? What happened whenever a small voltage changes takes place at either either one gate of the two transistors, either M2 gate or M1 gate. Okay, sir. Look at now. If Vin rises by delta V, suppose if you consider each case separately, treat each case separately, and it's important. So if Vin is raised by delta V, suppose, see, look at this picture. Here is myself is some voltage change is applied at the gate of M1. So what is the role of M1 transistor? M1 role is for any specific changes in the input voltage, there must be a corresponding current should flow in the drain. That is the role of M1, as it is a CS amplifier or CS phase. Okay, if V is raised by delta V, then the amount of the current flows in the M1, let us say ID1, and amount of current is flowing in the second transistor is ID2. Of course, both are connected in the series. Definitely ID1 and ID2 both are same. But we'll discuss later about this equality condition. But now at this moment of time, I'm talking about only the M1 device. So my question is, suppose if there is a delta V change applied at the gate of the M1, okay, so there must be a corresponding drain current changes. So definitely, for example, it is incremental value. If it is incremental value, of course, delta V is the incremental value. Okay, so for example, earlier it may be a 2 volts applied. Now delta V may be a 0.2 volts. 2 plus 0.2 is equal to 2.2 volts. You increasing some voltage at the input side. So definitely there must be a obviously there is a increase of the drain current. Okay, so if V rises by the delta V, then the ID1 increases by the how much amount of drain current is increases. Okay, so as we know the one condition, that is what? So your GM value is nothing but what? Change in ID by change in VGS. What is the VGS here is, let us say Vin. Okay, so that ID1 is increased by what amount of what factor? What factor? See, let me write on the board. Yeah. So this is my your GM value. GM is equal to so dou ID by dou VGS. Yeah, this is. So myself is I want to find what is the change or how much ID is increased, so that I can write dou ID is equal to GM is multiplied with dou VGS. What is the VGS? VGS is the input voltage. So that I can write GM1 because of I am talking about M1 device, and how much changes takes place at the gate delta V. So that is the change in ID. That's it. Yes, very simple to understand. Don't forget the basic equations. If you forget, I can't help you. Okay. Is it okay?
Yes, sir.
Yes. So now, okay, this change in the current flow to the impedance seen at the terminal X. This is my X. This is the node. X is about the node. This node I'm talking about. So since the change in current at this point is the GM is multiplied by the delta V. Okay. So the change in the current flows to the impedance seen at X. So seen at X means, I think, what is that one? I told you in the previous class, we have to see the input impedance and output impedance. If you want the output impedance, look down. If you want to see the output impedance, input impedance, yeah, look up, and output impedance means look down. Okay. So based on the theory, here I am taking the advantage to explain that at node X, the input impedance or the impedance seen to the from the X. Please stand at X. You should be stand at X. Stand here and look up. That is called the input impedance of the M2 device. Input impedance of the M2 device. So that the impedance seen at the terminal source of M2 is equal to the 1 by GM2. 1 by GM2. So GM2 is the transconductance of the M2 device. Okay. The amount of the input impedance, okay, of the M2 from the X, you can say that 1 by GM2. Okay. So next, thus Vx falls by amount given by delta GM1 into delta V by 1 by GM2. So what is this? This is the ID changes. What is this one? This is the impedance. Okay. So I think impedance and current is multiplied. Okay. I into, yeah, V is multiplied. Then we will get the, so yeah, I into R, sorry, is equal to V. V is equal to inter. Here V means the voltage across X. So that is Vx is equal to I means change in current in the M1 device. How much change it takes place? Already I calculated that it is a GM1 times delta V. Okay. Now impedance R of this device is nothing but 1 by GM2 value. So this is the what amount of the voltage changes takes place at the node X because of change. Okay. So incremental change takes place at the gate of the M1 device. Any doubt? Yes, I need the feedback. Do you have any doubt? Otherwise, I can move.
No doubt, sir.
Okay. So I hope you so note down these things. Yeah, next. To change in ID1 also flows to the RD. Produce the drop of GM1 delta V RD in the output. Yeah, of course. This is what stays. This is the CZ stays. What I told you, here is some voltage changes that already we calculate. That is the change or the node X value is equal. Simply I can write Vx value is nothing but, so GM1 is, so GM1 by GM2 into delta V. This is. So later, the same, whatever the current changes, ID1 changes because of both are connected in the series. So definitely this current is flowing into this device also, so that this current will constitute a drop across the RD, so that the output voltage also changes, corresponding changes because of the corresponding gate voltage changes. Because delta V changes, output also changes. Because input changes by amount of delta V, output also changes. But how much value changes, that we want to find. So simply, you know the current, so that current is nothing but this much. What is the current? GM1 into delta V is the current that is flowing in the two devices. And now the drop across this fellow is nothing but is multiplied with the load resistance RD. If you want to take the output, V out is equal to, what is that one? VDD minus the drop across RD. That is nothing but, so V output. Got my point? So it is, suppose if you check this equation, this output equation is very simple, and it is simply looking like what? CS stage amplifier output equation. Am I correct? Ramakrishna garu?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. I am here, sir.
Yes. So next one. Okay. Consider the case where Vin is fixed. I have already told you two things. We have two gates, M1 gate, M2 gate. M1 gate is fed with the input signal, and M2 gate is fed with the VB voltage, fixed bias voltage. Okay. In the first case, I have considered VB is constant, Vin is varying. That is the M1 gate is senses the change in voltage of delta V. So based on, because of that, there is a change in voltage in the output. We already calculated that. Now, another case is fix the Vin and talk about VB changes by some amount of voltage. Then what things will be changes there? Okay, consider the case where Vin is fixed and VB is increased by the delta V. Since VGS1 means what? Gate to source voltage is constant. So that means M1 device. This is the gate. This is the source. Okay. So since in the second case, this is constant. So definitely this is constant because source is grounded. Okay. Source is grounded and gate is fed with some constant voltage. Then VGS becomes constant. whenever VGS is constant, okay, so VGS1 is constant and R01 is infinite. We simply simplify the circuit as shown below. This is the, whenever this is constant, M1 device VGS is constant, whose this resistance. Generally, we will treat the transistor resistances, output resistance like this R0. This is infinite because that this is not allowing any current, or it's allowing a constant amount of current. You can take anything. Okay, this is infinite. We simply the circuit is whenever this approximations are takes place, this circuit I can redraw like this because M2 is there, RD is there, of course, whose gate is carries with the what change of some voltage, and the entire bottom device is replaced with a constant current source. Yes. How do Vx and Vout changes here? In earlier case, M1 what is it one? Gate is having some change in voltages, and M2 gate is carries with the fixed voltage. Now it is volta. Okay, because of changes of the takes place, you changed it. M1 gate is already fixed. M1 gate is at a constant value, constant voltage, and M2 gate is variable. That means some changes takes place. The voltage. Okay, then what happens? As far as the node X is connected, M2, see this is M2, this X node is this one. Okay. Source, it can act as a source follower because it senses an input to delta V and its gate and generates the output X at X. Here is, I'm talking about X, this X. What is source follower? Source follower is nothing but it is here is having some resistance. So source is carries some resistance. Here is some resistance. So generally you will collect the output is here. Okay, that is a source follower. But now, so in this circuit output is carrying here, output is you are collecting here. But when I am talking about the, suppose if you are trying to sense any voltage at the X node, then it is looking like a source follower. Okay, then we need to find the voltage change at the node X. So again, once again, so wherever you want to make it simplify, definitely we should forget about or neglect the two things. One is the body effect and one more is the channel length modulation. So again, for my convenience, I make both lambda and gamma or zeros. So then the small signal voltage gain of the voltage follower is equal to, what is the voltage follower? Voltage follower is buffer. So buffer, what is the gain? Of course, ideally we can speak it as a one unity gain. Okay, so what happened now? Okay, when we are thinking like treating the circuit as the voltage follower, what about output terminal? Yeah, because there is a RD load is there, you are trying to collect the output. So that whenever lambda, gamma both are zeros, then we talk about the small signal voltage gain. The voltage follower or source follower will be definitely have a unity gain. Means whatever the input voltage of the M2 takes place, there must be a corresponding changes in the X. The equal amount of changes will take place in the X. Then the gain is 1. Okay. So whenever we are talking about this node X voltage, so just forget about the drops across the RD like that. So this makes Vx will rise by the some value of delta V. Here the change is delta V. Here also changes delta V. As per the source follower theory, what happened? Definitely the gain means the change in output voltage to the change in input voltage. Definitely 1. So that's what I'm talking about. I'm talking just very simply. I kept to write as the voltage at X point X because of the change of the gate voltage delta V is same as delta V only. So that is, on the other hand, output does not change because of ID2 is equal to the ID1 and hence remains constant. Yeah. Okay, this is okay because of M2 gate potentially changes by some amount. There is a corresponding and equal changes takes place at the node X. And since ID1 is constant, of course, ID2 is also constant, both are equal and they are constant. Output won't change. Whatever the earlier output you have for the fixed input voltage, we will get the same thing. You get the same voltage, no change. But at X, you will find the corresponding changes. Two things you can observe. One is when M1 gate is variable, M2 gate is fixed, then for the corresponding changes of the voltage at the M1 gate, definitely the corresponding changes will take place at the output. Whereas in the case of if M1 gate is fixed and M2 gate is carries the change in voltage, then there is no changes will take place at the output voltage. Okay, that is the two things we should remember. Yeah, any doubt, please?
No, sir.
Understand?
Yes, sir.
Ramani garu. No? Vidyasri. Hello? Sushma.
Yes, sir.
Hello? Suresh. Suresh. Are you in meeting?
సార్ ఎనీ ఇష్యూస్
ఏమండి?
ఏమైనా అయిందా సార్ అంటే పిలుస్తున్నారు
ఏమన్నదండి మీరు క్లాస్ ఆన్ చేసి పక్కన పని చేసుకుంటున్నారు పిలుస్తున్నాం
సార్ లేదు సార్ ఇక్కడే ఉన్నా సార్ ఇయర్ ఫోన్ ఊడింది చెవులో అంతే
ఓకే ఓకే ఏమండి విద్యాశ్రీ రోల్ నెంబర్ 10
Sir, I'm listening, sir, but my data is not that
Data
much
problem. Okay.
connected.
Pratyusha.
Hello. Yes, sir.
Expert అవ్వాలి. Ashik.
Yes, sir. Present, sir.
Any doubts, please?
No, sir. No, sir.
No, sir.
There are two cases here. Yeah, please. Yeah, please. Somebody is asking some question. No? Okay, anyhow, in the Cascode, two things I have observed. What happened if M1 base is having some changes in voltage and M2 gate is constant at that moment of time. And second case is if reverse, M2 gate has a variable voltage and M1 is having a constant voltage, then what happens? So I have things very clear that as I said, so in the first case, definitely you can find the corresponding variation or changes in the output voltage, but in the second case, you won't get any variation in the output voltage. Yeah. The next one. Yeah, now the study the bias conditions of the cascade. So still definitely this is my again bias voltages means what is the voltages across each and every terminals. Okay, here I am keeping like this. Yeah, this is M1 device. Wait a minute. This is M1 device. Okay, I think whose gate is carries the input voltage. Okay. Then gate and this is the drain. This is the what VTH1 voltage in between plus and minus, and then corresponding here and here. So here and here voltage is how much voltage this one here is between this drain and source of M1 is you can write VDS1 is equal to VGS1 minus VTH1. VGS1 means this is the gate and this is the source. This voltage minus this voltage is nothing but this voltage. Yeah, you can write like this. Otherwise, yeah, this is the VGS1. VGS1. Oh, VGS1. Yeah. So maybe this is minus, this is plus. You can say minus to plus plus, plus 2 minus minus. So this is different. This is the VDS. VDS1. So you can write VDS1 is equal to, so VGS1 minus VDH1. This is the condition. Okay. So for M1 to operate in the saturation. So what is the condition of the saturation? Let us say this is the X voltage. This node voltage is X. So generally, saturation condition is VDS must be for greater than, so VGS minus VTH. This is the case. This is the case. So you know about this VDS, that is the VGS minus VTH1. Then this voltage must be less than the Vx. Then this device is keeping in the saturation. Very simple. So if you suppose if you have some numerical values, then you should calculate the Vx value and evaluate the VGS and VTH values. Then take the subtraction and find the difference. What is the find the comparison of Vx and VDS1. So if Vx still greater than the VG, this our exit voltage or effective voltage, then definitely our device is in the saturation. If it is below, then you can say that your device is not in the saturation. Okay, this is the condition. I think it is very simple to understand from this picture. Okay, so how you can write? Yes, and one more thing. If M1 and M2 both are in saturation, M1 and M2 both are in saturation, M2 operates as a source follower. M2 operates, suppose both are in saturation, whenever it's saturation, okay, so VGS3, Nara, VGS3, yeah. VGS3. Nara, madam? Hello?
సార్ తను జాయిన్ అయింది సార్ ఇందాక యాక్సెప్ట్
అందరూ కనిపిస్తున్నారు కానీ ఎవరు రెస్పాండ్ అవ్వట్లేదు.
విజయశ్రీ ఉన్నారు లాస్ట్ లో, విజయశ్రీ దోమాదులా అని ఉంది కదా.
ఏంటి రామకృష్ణ గారు
సార్
మీరు చెప్పండి దిస్ స్టేట్మెంట్. సో ఇఫ్ M1 M2 both are in saturation, M2 operates as source follower, what does it means?
సార్ మళ్ళీ ఒకసారి.
Both are, I think statement is on the slide. If M1 and M2 are in saturation, both are in saturation.
M2 operates as source follower.
Yeah. How we can say? So whenever both are in saturation, I can replace this M1 transistor with the constant current source. Then simply it is a source follower. Am I correct?
Yes, sir.
So whenever both are in saturation, I can replace M1 with the constant current source. Am I correct?
Yes, sir.
Yeah, then it is source follower, simply source follower circuit.
Yes, sir.
Yes. So, yeah. So next, whenever I think it's a source follower, then how can you find the Vx value? So then Vx is equal to, again, I'm talking about Vx value, is equal to, whenever this is current source, I could not find the voltage across this fellow, so that I should manage the X value or voltage at X value with the M2 terminal voltages. Am I correct? Say yes or no?
Yes, sir.
Yes. So that I can manage like this. Yes. Now Vx is equal to VB. Yes, of course, VB minus this drop. What is this drop? So VGS2. Okay. Get to source of M2. So this is my Vx. Earlier my Vx is, this is the condition of Vx to make the M1 in the saturation. If it is saturation, okay, M2 is also in saturation, but M1 should be replaced with a constant current source. Then it becomes source follower. Then I can find the node X value, voltage, or node X voltage, Vx is equal to, because this is already replaced with the current source, I could not say what is the amount of voltage across it. So that I need to manage, I need to calculate the voltage at X point with the help of M2 terminal voltages. So that it is simple to understand now. Simply Vx is equal to Vb minus Vgs2. Fine. Okay, if it's fine, then I will go for the next statement.
Yes, sir.
Since this is the Vx,
Yes,
I think in the second case, yeah. So this is the Vx. Okay, in the second case, this is the Vx in the first case condition. So according to the rules, means saturation rules. Okay. So in the second case, you calculated the Vx value as V minus Vgs2. In the first case, you took one condition to keep M1 in the saturation. That is, okay, Vx should be greater than, okay, V in minus or Vgs1 minus Vth1. So that I can write this as Vx is greater than, so V in minus Vth1. Of course, Vn is nothing but Vgs1. Don't forget about this one, minus Vth1. Okay, this is my condition. In the next case, I found this Vx from here. So that now I can substitute this value, Vb minus Vgs2 should be greater than, so Vgs1 minus or Vn minus Vth. Nothing wrong to write the, so in place of Vgs1, Vn, because so the gate potential and the source is grounded. Vgs minus V1, Vgs is nothing but Vg minus Vs. Vs is 0, Vg is Vn. So that nothing wrong to write or replace Vgs as the Vn. Yeah, this is my condition. Am I correct? What is the condition to keep V1 in saturation? Sorry, M1 in saturation is what? So Vb minus Vgs2 is should be greater than what? Vgs1 minus or Vn minus Vth1. Are you okay?
Yes, sir.
Are you okay or not? So definitely to measure the saturation region of a transistor, definitely we should look at its drain potential, because if its drain potential is more than the effective voltage or excess voltage, definitely your device will be in the saturation. So based on that, so I'm talking about this is the condition. This condition is for the only M1 transistor. The same condition I need to check for the M2 transistor also. So what is the M2 drain current? Sorry, drain potential. I think because of V out is there, I can say this is the V out. So M2 should be in the saturation. Your V out should be greater than whose effective voltage? What is the effective voltage? Vgs2 minus Vth2. This is. What is the Vgs2 once again? Vgs2 is nothing but this difference. Vb minus Vth2. Vb minus Vth2. You can say. That means V out should be greater than, so Vb, okay, minus Vth2. That's it. You got my point, sir? Two conditions I have written here. Two conditions I have put forward for both the transistors in the saturation. So it's very simple. I think there is no clumsy here. That means whenever you want to find the transistor region of operation, check its drain voltage. Okay. If its drain potential is more than the what? Its excess voltage or effective voltage, definitely your device is in the saturation. Otherwise, so don't say this is in the saturation. I hope this explanation is enough for you.
Yes, sir.
Yeah, this is thing I wrote here. V out should be, V out is what? Yeah. So I'm talking about the M2 saturation. V out should be greater than V in minus Vth1 plus Vgs2 minus Vth2. Yeah, total voltage. I'm talking about total voltage because This potential is V out potential is, this is the drain potential, I say, this value should be more than this voltage. Already you know about this one, and already you know about this one. Okay, otherwise you can write this Vx minus this thing. Okay, so that VGS Vin minus VTH1 plus VGS2 minus VTH2. You can separate, I think Vin I can write VGS1, okay, no problem, minus VTH1 plus VGS2 minus VTH2. This is okay. This is the case. Now, yeah, if VB is the what? The amount of the voltage, fixed voltage applied to the M2 gate is chosen to place M1 at the edge of the operation, edge of the saturation. Okay. Suppose if you apply the voltage VB in such a way to produce the corresponding voltage at the X to keep this M1 device at the edge of the saturation. At the edge of the saturation. Understand? Myself is the device saturation or cutoff or a triode region is fully depends on the voltage applied to the gate. Okay, so now myself is thinking that whatever the potential is applied at the gate of M2, okay, which is insufficient to make fully M1 in the saturation. This may be at the wedge of the saturation. Okay, what happened? That means our Vx value changes. How much it changes? Okay, if VB chosen to place M1 at the edge of saturation, so consequently, the minimum output volt level, okay, the minimum output level, so for which both M1 and M2 operate in the saturation is equal to simply by looking the above equation, what is exactly explained now, just now. If you see this two, I think what this is this VGS1 minus VTH1 is the effective voltage of the or overhead voltage of the M1 device, and this is the overhead voltage of the M2 device. Very simple. From the above equation, I can write, I can conclude that overdrive potential of V1 plus V2. Understood or not? Whenever VB is chosen to place M1 at the edge of saturation, so what happened? The minimum output level for both the transistors to operate at the saturation is equal to the addition of the overdrive voltages of both M1 and M2. What is the overdrive voltage or excess voltage or effective voltage? Oh, everything is same. Effective, overhead, overdrive, or
Excess voltage.
The three terms are same. Don't confuse with the terms. Okay, simply M1 overdrive potential plus M2 overdrive potential is required to keep both the transistors in the saturation. That is the minimum voltage required. Your output should be at least equal to the what? M1 overdrive plus M2 overdrive. This is the condition. If you violate this condition, definitely your output should be lagging below the M1 plus M2 overdrive voltage. Then I think your two devices will not be in the saturation. Got my point?
Yes, sir.
The minimum voltage, minimum output voltage I'm talking about. So output voltage, who will produce the output voltage? Input voltage will produce the output voltage. Based on the input supply, you will get the output voltage. The minimum output voltage should be required to keep both the transistors in the saturation. Is very simple to understand that sum of the each overdrive potential. Got my point?
Yes, sir.
Yes. So I don't want to repeat once again. This is the things. Next. Yeah. So whenever this situation is occurring, like this overdrive potential, sum of this one, I can say one word. I think mostly this word is very useful and a very popular word which is used in the research terminology. M2 is stacked on the top of M1. What is the meaning of this one? Stacked. M2 is stacked on the top of M1. So generally, there are many techniques to reduce the power in the device, in the circuit. Whatever the circuit, you can take low power techniques. Low power techniques. There are many more techniques are there, but one of the techniques is stacking approach. What is the meaning of stacking approach? I think here, if you see the two devices M1 and M2, both are, of course, NFETs. Okay. Huh?
Yes, sir.
Both are NFETs. Okay. Yeah. So myself, I'm talking about M2 is stacked on the top of M1. This is called the stacking approach. Stacking approach generally how we are doing in the what is that one implementation is. For example, one transistor is there. This is my one transistor. Yeah. This transistor should be replaced with the two transistors which are connected in the cascode configuration like this. This is called the stacking operation. What you can achieve from this? So whenever you split one transistor or whenever you replace one transistor with the two transistors, okay, what happened means, for example, this aspect ratio of this device is W by L is equal to L is fixed, of course, maybe a 90 nanometer technology. If you take this is 180 nanometer, so W is maybe 180 nanometer and 90 is the W is the 180 nanometers and L is the 90 nanometer. Okay, this is the one transistor. What I am doing here is, in this place of one transistor, I want to keep the two transistors with the same length, and but with this half. Means this is 90 by 90 and this is 90 by 90. What is the advantage of this one? The advantage is, earlier the device is big size, now the size of the devices reduces. One thing. And definitely the longer devices are stronger devices. Strong means in the sense of having more dimensions. Understand? Strong and weak devices. The meaning of strong and weak is nothing but strong means whose width is more. Weak means whose width is less. Okay. The strong devices generally will consume the more power than the weak devices. Okay. So whatever the power consumption by this device, obviously less in this configuration. This is called the stacking approach. Generally, we use the stacking approach in the low power, is one of the low power technique. Understand, Babu?
Yes, sir. Yes, sir.
Huh? So here is, that is the meaning of stacking. So I am, by this configuration, I'm saying this configuration, I'm looking this configuration, I can say M2 is sit over the M1. That is the stacking of the M2. Got my point? Okay.
Yes, sir.
But the stacking approach is very old approach. So now nobody is using. But earlier it is a one of the wonderful technique to reduce the power consumption of the device. Okay. Now, so analyzing the large signal behavior of the behavior. So whenever Vin goes from 0 to VDD, yeah, this is my voltage characteristics, input voltage versus output voltage. For example, my input voltage is 0. My input voltage is 0 in the previous circuit. What happened? Definitely, none of the devices in the saturation. None of the devices in the saturation. No current, so that no drop across RT, so that full VDD will be appear at the output. So this is that's why when Vin is 0, your output is VDD. Am I correct? Please remember the circuit. I don't want to go back. Okay. So in this circuit, there are two devices M1 and M2. Suppose whatever the voltage, input voltage applied is 0, definitely the output may be a very small voltage. So that no drop something, V out is equal to VDD, you will get the full. For V in is less than the VTH1, this case, this region. Yeah, 1 second, 1 minute. I want to, yeah. This region, this is the VTH1 voltage. Now, suppose your input voltage is less than this region, this region, for example, your input voltage is in this range. What happened? So, input voltage is less than the VTH means go back to circuit. So, input is applied to this one, so that this device will be in the off condition. This device will be in the off condition. So whenever this device is off condition, okay. So what happened? Still, your output is at VDD only because no current. So because the two devices are connected in the series, if one device off means no current will flow. So that your output is VDD still. Okay. So and you can find this is the V out curve and this is the Vx curve. Okay. So earlier, whenever input is 0, input voltage is 0, your Vx values, voltage at x is equal to, node x is equal to VB minus VTH2. Already we calculated. It will be maintained up to VTH1. Once VTH1 input voltage is above the VTH1, the M1 device will go into saturation. Whenever M1 device is in conduction, then definitely currents will flow, which will establish some voltage drop across the RT, so that definitely your output voltage will decrease like this. So whenever your output voltage decreases, definitely your Vx voltage also decreases. Am I correct?
Yes, sir.
So for V in less than VTH, M1, M2 are off. Okay. So V out is VDD and Vx is VD minus VTH2. Suppose if you neglect the subthreshold conduction. What do you mean by subthreshold conduction? So means the amount of current flowing when the devices are in the off condition. Okay. If you neglect that, this is the 5. Suppose when your input voltage exceeds the VTH1, so M1 starts to begin and makes the voltage drop across RD, which makes the output voltage cooling down and Vx also cooling down. Both are cooling down. Since IVT increases, VGS2 must increase as well, causing Vx to fall. As Vin, so increase very large value. See, this is the large value. I'm talking about this reason. I think sufficiently the input is large applied. You can find the two things. One effect is Vx, the node X voltage, drops below the Vin by VTH. Vx voltage is Vin minus VTH1. So whenever Vx value is below, let's say this Vx value, 1 minute, I will write here. Yeah, your Vx value is 4 less than the what? So Vin minus VTH1. What is this case?
Region, sir.
Vx means what? VD of M1. VD of M1. If VD drain potential is less than the overdrive potential of M1, what happens? Definitely it is not in the saturation. Then what? Which reason? Deep triode region or triode region? It is a triode region.
Yes.
Triode region. So whenever the situation occurs, your M1 device will go into the triode region, not in the saturation. So out of the two effects, one effect is, okay, so as Vx fall down, if it is less than the overdrive potential, your M1 will enter into the triode region. Okay. Similarly, the second thing is, effect is output voltage. Vout means M2 drain voltage, which also drops below the VB minus VTH2. VB minus VTH2 is the overdrive potential of the M2. Okay. Since Vout, your output voltage, Vout is less than VB minus VTH2, what happened? Again, your M2 device is also not in saturation. It also comes to the triode region. These two things we can observe with this case. What is the case? Suppose your input voltage is what? You are increasing to the large extent. Then we can find the two observations. By that way, you can conclude that the two devices will be cooling into the So triode region instead of the saturation region. So depending on the device dimensions and the value of RD and VB, one effect may occur before the other. So I think both will not come at a time. So one after another will come. Okay, that depends on the what RD value and aspect ratios and passing voltage. Yeah. So I hope you understand these two things. ఏమండి అర్థమైందా? హలో
Understood, sir.
Yes, sir.
The condition ఏంటంటే from this characteristics I'm going to explain what happened if input voltage is 0, what happened if your input voltage is less than the VTH1, what happened if your input voltage is greater than the VTH1, what happened if your input voltage is far greater than the VTH1. These are the conditions. I started my journey with both the transistor and the saturation. Then, because of this, V in this input voltage increases, to a large extent. Okay, my transistors are pulling into the triode region instead of keeping them in the saturation. So very simple to understand that the device of reason of operation, check the drain potential. Okay, so if the drain potential is more or less, check it, than the overdrive potential. So if the first condition, saturation, if the second condition, triode region. Okay, understand?
Yes, sir.
Yeah. The next one is I'm talking about. Okay, so what changes takes place about this cascoding the devices already observed. Now it's time to find what is it one? Draw the small signal model and voltage and impedances find. Yeah, this is the point of time to discuss. Okay, this is the small signal characteristics of the cascode stages. See, this is circuit. This is one device, and this is another device. So in the one device, that means M1, you're applying the input voltage. So from gate and source, you have V1, gate and source, and drain. Okay, drain of M1 is connected to the M2. So that this is the M2. And load is also with M2. So this is a small signal model. Okay. And అర్థమైందండి? Hello?
Yes, sir.
Mahati,
Sir.
yeah, do you understand?
Yes, sir.
Yeah. So this is the point where this is circuit. We need to find the voltage gain, and input impedance and output impedance of the circuit. Okay. So I think so. Please look at all these things. Then in the next class, Monday class, we'll discuss about this parameters calculation.
Okay, sir.
Okay. Any doubts? Please rise now. Yes, I'm waiting for doubts. If no doubts, I will stop the meeting.
No doubts.
Thank you. So, Madam Niku.